Good morning. Here we are back in lab, and this week we are looking at a lab dealing with radioactive decay. So we're going to be looking at a topic referred to as absorption length. And that says that if we have some kind of a radioactive source, we can get out a Geiger counter and measure what the rate of decays are that we're picking up. And then what we can do is take some kind of a material and use it to block some of the radiation. So we could use some kind of a material and find out how effective that material is at absorbing whatever type of radioactive decay that we're dealing with. And so for us today, we're going to be measuring the absorption length, which is going to tell us, we'll talk about what that means, for aluminum, iron, and lead. And what we're going to be using in terms of a radioactive decay particle are 662 keV photons. Now, where that's coming from is the beta decay, the beta and then gamma decay of cesium-137. So if we do an energy diagram, what we can say is we start out with cesium-137. Now, cesium-137 is radioactive. And it first of all undergoes beta decay. Now, when cesium-137 undergoes beta decay, it's going to turn into barium-137. But there is an excited state of barium-137. So what does that mean? Well, it says that even though it's barium-137, and it's got 56 protons and however many neutrons, not all the protons and neutrons have settled down into the lowest available quantum states. So this decay typically happens in two steps. First of all, there's the beta decay, where we have, and we've been talking about these in class. So in the beta decay, one of the neutrons inside the cesium-137 decays into a proton, and the coupled reaction with that is the formation of an electron and an anti-neutrino. It's actually an electron neutrino, which we'll talk about more in chapter 44, or chapter 43, I guess. So when this decay happens, now it's barium-137, but again, the protons and neutrons haven't settled all the way down into their lowest quantum state. So probably a neutron drops or a proton drops into a lower state. And what that does is it releases a photon. So the same way that electrons in hydrogen, I guess, is the example we've looked at the most. An electron drops to a lower state, photon gets released. Well, the same thing is going on in the nucleus with the individual neutrons and protons. Now, it turns out that 95% of the time, the beta decay leads to this excited state, and then that is followed by a gamma decay. Now, the electrons that are generated in beta decay, they don't really travel through material very well. Electrons, a sheet of paper or something, is probably enough that the electrons interact with all of the other electrons in there, and they're slowed down and stopped pretty quickly. The photons, however, that are released in gamma decay, those can travel longer distances. And so what we're seeing here is we're going to start off with different thicknesses of, we have some aluminum samples. Here's some aluminum samples. These are each about a centimeter or about 10 millimeters in thickness. And so what we can do is sequentially, we'll put 10 centimeters, 10 millimeters, and then an additional 10, an additional 10, an additional 10. So as we increase the thickness of the aluminum, what we're going to ask then is, well, I have a certain rate at which decays are being observed before the shielding is put in place. What's going to happen to the drop-off? Now, this is just an example of what some of the data might look like. These are just some numbers that I've made up. So let's say that we do put a series of these aluminum discs in place, and with one aluminum disc in place, I'm measuring 252 decays every second. These are referred to sometimes as counts. So the counts here would be 252, and we're running we're running 60-second samples. So our detector is going to be measuring over a time period of 60 seconds and counting how many decays happen. And then you can see as we put more aluminum on that the numbers are coming down. Now, remember this is radioactive decay, so it's in some sense a random process statistically. There is a lifetime for each one of the radioactive isotopes, but around that lifetime, we're going to see statistical fluctuations take place. Now, statistics for radioactive decay, they follow what are called Poisson statistics. Maybe you've seen this in a statistics class. Very likely you haven't run into these before. Poisson statistics deals with events that happen in some number of occurrences. And so what we find with Poisson statistics is the fluctuations that we see are given roughly by the square root of the number. So the way this would work is, let's say we measure 252. Well, how much fluctuation would we expect if we did a whole series of measurements? We're not going to get 252 every time because the radioactive decay process, in some sense, is going to be random. So the way we would estimate what size fluctuations we would expect is we take the square root. Now, 252 turns out to be very close to the square of 16. When we take the square root, we get 16. What is it? 16 times 16 is 256 or something. So that works out to be 16. Now, as the numbers go down, notice that this square root effect drops off like a square root. Now, we're going to use those to generate a graph. So here are the counts, or the numbers of decay that we're observing each minute. And then along the horizontal axis, we'll put down the thickness of the material. Now, we'll first of all do this with aluminum, with these discs. And then we'll follow up and do a series of measurements with some iron discs. And then, I don't have those with me here, but back on the table where I've set this up, there are some lead discs that we can also use. There's some lead samples of lead of different thicknesses that we can use to go in and get some measurements on the lead. So we'll get a graph for each one of those. Now, the way that absorption works is we expect, both theoretically and then when we go into the lab, we observe this experimentally, that the number of decays that we measure drops off exponentially with thickness. Now, this might look kind of like the radioactive decay rate formulas, but it's not the same thing. When we were looking at radioactive decay rates, those were in terms of time. As time went on, the radioactive decay rate dropped off. This is in terms of thickness. So mathematically, they do look very, very similar. But remember, this is thickness of material, and then the scaling factor that determines, how much material would I need to have the decay rates or the observed number of decays drop by a certain factor is referred to as the absorption length. Okay, so that has units of length. Now, we can work directly in terms of the exponential formula, or as an alternative, we can work in terms of natural logs. Now, the advantage of working in the exponentials is you can actually see the numbers, and the graphs, you can see this exponential drop-off, and you can do an exponential fit. If you use the logarithm approach, I'm taking this formula and just taking the logarithm of both sides, this actually turns out to be a linear fit. So you can try this either way, and I'll make sure in the slides for the lab, I'll put in some examples of data tables for both. I think I didn't quite have room to get everything on the board for this, but I'll put some of those examples into the slides, so you guys will have those. So where are these error bars coming from? These are the data points, these central values. But notice that I've put in what are called error bars. So these show up in all kinds of graphs. they certainly work well for today's lab, because what we're saying is that even though we measured the 252 number, we know just by the statistics of radioactive decay, that number could have been higher or lower easily by 16 or more, okay? So the size of the error bars represents what we consider to be one standard deviation or one of these statistical fluctuations. So I want to make sure that the error bar is representing plus or minus 16. And then for the next data set, this is at 203. The data bars on this one are going to be plus or minus 14, plus or minus 13, plus or minus 12. Now, depending on what applications you're using to generate your graphs, the applications may allow you to put error bars in, or you may want to put them in by hand, or you may have to put them in by hand. So again, you can put the central data values in. Those are the ones that are listed on R. And then to get the size of the error bars, look to see if your application allows for that. If it does, fine. If it doesn't, just write the error bars in by hand. So pay attention to the vertical scaling to make sure that you're accurately representing these variations in R. Now, if you're doing this with the logarithm approach, what will happen then is you're working from this formula. So this formula right here corresponds to the graph that we have here. And in this case, the formula we get is linear. The y-axis, instead of being R, on this example, the y-axis is R. On this one, the y-axis is the ln of R. So instead of plotting R versus X, if we take the this logarithm approach with the using the ln, then we'll be plotting ln of R versus X. And by readjusting the scaling on the vertical axis, we're able to take what was an exponential function and represent it as a linear function. So, and linear functions are, in some ways, they're more reliable visually. So if the data doesn't end up in a line, I'll probably pick that up right away, right? If I'm doing a lab or something and my data doesn't line up. If my data is exponential, then I don't see that immediately. I have to put one of these exponential functions in to see if things really do line up or not. With the linear fit, it's quicker to be able to look at your data and see if, but either approach works. So you can take either approach is fine. This is a good example to go in and try out some exponential fits. Now again, because of these statistical fluctuations that are going to be occurring with radioactive decay, the data points are not going to all line up. In fact, I drew that this is too idealized. I would actually expect that some of this data is not really going to line up with that exponential fit very well. That's just the nature of radioactive decay. Here, maybe I did a little better job. This one is off the line a little more. This one's off the line a little more. So if things don't line up perfectly on this one, don't panic. Put your error bars in. Now, once you've got the error bars in, and if things really don't line up still, then you can panic. Or better yet, stop by office hours and let's take a look at your graphs and see if things look fine. A lot of times students panic a little bit and they go, it just isn't lining up, but it's perfectly consistent with our understanding of the nature of radioactive decay. Other times there are problems, so definitely if you've got questions, stop by. Ultimately, what we're after for each one of these samples is a measure of the absorption length. So we want to get an L value for aluminum, iron, and lead. Now on the logarithmic graph, that value of L is going to be the inverse of the slope of that line. On this graph, the L will be the inverse of whatever coefficient your fitting application does for that exponential fit. So now if you're doing these graphs by hand, I would suggest going the logarithmic route, because you're not going to be able to draw an exponential fit by hand, but you can draw a straight line by hand pretty readily. So we'll get those values of L, and then the R0 values, when you look at the data table, notice that we're not doing a measurement with no shielding in place at all. Why is that? Why aren't we taking some measurements with zero shielding? And that's because we don't want to have the background of these electrons. So if I don't put any shielding in there at all, there's a good chance that these electrons will show up in enormous numbers. And what we want to do is just limit ourselves to the gamma decays. The gamma decays are going to be able to travel through much thicker layers of material. If we're just looking at electrons, by the time we put in one disk of aluminum, the electrons are pretty much gone. And so we've got two competing types of radioactive decay, the beta decays and the gammas, and by working with at least one layer, starting with one layer of material for the aluminum, the iron, or the lead, that eliminates the effects of the electrons, so that we're just looking at one type of radioactive decay. All right, questions on any of that? I think that pretty much outlines what we're looking at. So let's take a look at the setup. Let's take a look at our samples and see what our Geiger counters look like that we're going to be taking the measurements with. All right, here we are at one of the tables, and what I've got out here is one of our measuring devices. This is actually a Geiger counter, and you can look at the screen here, and you can see that it's all ready to count a certain number of decays. Kind of the central feature for this is this Geiger tube that I will just set out here to the side and take a look at. So what this Geiger tube is doing is high energy particles are able to cross through the opening on this tube at one end. It's actually sealed, but there's a very thin layer of material at one end, and the high energy particles are able to pass through that, enter the chamber, and once the high energy photons or electrons are inside that Geiger tube, they will generate a brief current of electrons inside the gas that's inside the tube. It's argon or krypton or something inside there, and as the high energy particle passes through, it's going to generate a stream of electrons which will generate a brief current. Now what we've done over here with this unit, the Geiger tube is plugged into it, and I'm going to go through the display here. So what I've done is, for the Geiger tube, I've set up a voltage of 900 volts. Now that's pretty high voltage, but it's not much in terms of charge. What we've done is we've set up a voltage on the Geiger tube. So the Geiger tube has a surrounding cylindrical surface, and then it has another conductor that runs down the middle, and we're maintaining a 900 volt difference between those two electrical conductors. So if just a little bit of current gets generated, this 900 volts turns that into enough current that we're going to be able to easily measure what's going on. Now what I also have right here next to the Geiger tube is we have our sample of cesium-137, and so I'm going to try picking that up. We have these little handlers, but this is what the sources look like that we have, and I'm just going to flip this over. On this side you get a better view, so you can see that it's just a tiny amount of radioactive material that's been embedded in plastic. And what we want to do is take this cesium-137. Now the cesium-137 is really just in the center portion of that disk. So I'm going to move that into our counter device. Now what I'm going to do then is I'm going to take the Geiger tube that we've got right here. I'm going to pop off the top of that so you can get a closer look at the end. So again, there's a thin layer of material that the high energy particles are going to be able to get through. I'm going to place that into that support structure. Now what that provides for us is a fixed distance, so a fixed consistent distance between the sample that we have inside here and where the Geiger tube is located. So now what we can do is, oh, here's all my iron discs. There's a bunch of aluminum discs here. And then over here are the lead samples. So these are actually coming from a more complete box of different samples. And so these are thicknesses that have been measured. And we're going to have to get the calipers out and double check the thicknesses on the aluminum and on the iron. So let's see how this works. I'm going to turn the displays to what we are calling counts. Now I've set it so that it's going to take 1 minute readings. So I'm going to reset this and then I'm going to start counting. Okay, so what you're noticing here is we're getting an enormous number of counts. So it's picking up a lot of radioactive decay particles. I'm going to stop this and then reset it. Now, what would happen if I took the Geiger counter tube out? I'm just going to place it on the table over here. So the sample's over there, my radioactive sample, and then here I just have the Geiger tube. Well, what happens if I count just what we would consider to be background radiation? So there still are particles that are coming through. I've got 4 right now. There's a 5th one. So there are high energy particles all the time being generated in the tiny, tiny amounts of radioactive material around us. Or it's just a high energy particle coming in from outer space from some kind of a reaction. So there's what's considered a background level. And you can see the backgrounds are actually quite low compared with if I take the tube and move it over to my sample. Okay, that's a pretty noticeable difference, right? All right, so I'm going to stop this. Now, most of the counts that we're getting right now are due to those electrons. The electrons have a much higher efficiency of setting off our Geiger tube than do the photons. And so let me reset this, and let's see what we get for counts. Oh, wait, stop. I forgot. I got to put some shielding in. So I'm going to take one of those aluminum discs. Okay, so there's just one of the aluminum discs. And then let's go back and see what the effect is for just one of the aluminum discs. And you can see this is a much more modest number of radioactive decays that we're picking up once we've got an aluminum disc in place, just one. And so it's blocking out, again, the beta decays, the electrons that we're picking up. The neutrinos, we just don't pick those up at all. They interact so infrequently. The electrons we can definitely pick up, the photons we can pick up. And now we're down to just those high energy photons, those gamma photons that we're picking up. Okay, so you kind of get an idea of what this looks like. I'm going to go ahead and, again, I'm going to stop and reset. Okay, so we get measurements with the aluminum discs in place, and then we'll stack those. So once I've got a measurement with 1 stack of aluminum, I'll go with 2 stacks of aluminum, and then 3, and then 4, and then 5. So we'll see how many, thicknesses of aluminum we can fit inside there. And then once we've got those measurements made, we'll move on to the iron. And then finally, we'll move on to the lead samples, and we'll get measurements for all of those. So, so that's it. That's what the lab looks like for the day in terms of taking these measurements. If you guys have questions, stop by, let me know. Once again, the time intervals, what we're doing is we're measuring how many decays we observed during, I think I'm going to go with 60-second. Sometimes, We'll see. I think I'm going to go with 60-second intervals. I might choose to go with 100 seconds so we get some larger values for those. But that's kind of the setup for the lab.